let's do this. So I'm really excited about this. So we're gonna talk about the Mandelbrot set. The Mandelbrot set is one of the most incredible things that I've ever witnessed. Period. I think you sort of have to experience it firsthand to get the full experience. And I guess part of why I want to do this session is to try to allow more people to see that. So one thing I want to show is some screenshots that I've taken of the Mandelbrot set.
Oh, what is this?
These are some screenshots that I took yesterday. So I built a Mandelbrot set visualizer and I zoomed into the world of the Mandelbrot set. And these are some of the images that I captured from that world.
Okay.
This is one of my favorites. What does this look like?
A galaxy, maybe?
Yeah. It kind of looks like a galaxy with two spirals. It's also got these, what do you call this? Medieval knight armor has these little protective layer, maybe. It also looks like a guy with goofy glasses.
It looks like a swirl. Just keep going in.
This one maybe looks like a big pond.
It looks like a volcano.
Oh yeah. It's got these tiny craters on the side in addition to the huge crater. This one.
Whoa.
This one could be lava, maybe, or it could be coral.
Sort of. It's like giant animal legs, but
like an elephant that has more toes than the normal elephant. This is like a jewel. It's like a decoration in a palace.
Yeah.
It looks like a gem in the center that's been cut and polished, and it's got this star decoration around it. This is another one.
So symmetrical.
Yeah, it is extremely symmetrical. One thing I want to mention is that these designs are not actually designed, as in I did not design these things.
I like this.
This could be like a pendant on your necklace.
Yeah.
This is another swirl pool galaxy kind of scene, which is really beautiful. So I was saying these are not actual designs. It was not designed by a human. Instead, it was all created with an algorithm using just one very simple formula. This one looks like a sunflower that's been infected by bugs.
I like this actually.
Yeah, it's like some of them are beautiful. Some of them are like pristine, clean, but some of them look very disturbing. This is actually the top level view.
Okay.
Of the Mandelbrot set. If you think of the Earth as this round sphere, this is us looking at the high level view of the Mandelbrot set. These images is like looking at different places inside the Earth. This could be a water body, maybe, with channels that are coming out of it. I don't know what this is. This doesn't resemble anything we see on Earth. Maybe some mountains or coral. Well, maybe like there's a lot of things we don't see, right, at the microscopic level.
Yeah.
So it could be that some of the things that we see here might resemble those things. So the Mandelbrot set at the top level looks like this. But if you zoom in, sort of the same way that we zoom in on Google Earth, then you find amazing, incredible pictures, the same way that we can find incredible images when we're zooming into Google Earth. There's so much complexity inside of it if you zoom into it. It's almost like a divine creation. Like a human could not possibly have created this because human minds are too limited. Another name people have given to the Mandelbrot set is the thumbprint of God.
Okay.
I'm going to teach you how to draw the thumbprint of God. You can read about it on Wikipedia. So I'm going to do this sort of like a step-by-step tutorial. This is going to be something like the final result. You only get the full effect of amazement if you write the code yourself. So even you, Huiqi, if you have time later, I recommend you do this yourself afterwards. There might be some people that prefer to figure things out themselves. And if you want to do that, I recommend these two videos in the center from the Numberphile channel. Watch one of these two and see if after watching that, you can reproduce the Mandelbrot set in code. And then after that, you can come back to my video and compare notes with me. So without further ado, I'm gonna make a very basic HTML file. Maybe with a head. Maybe the head has some style. I'll need some styles later. And I'll have a body. And we'll have a canvas. I'll give it an ID of canvas. Let's also add a label, which later on we'll use that for diagnostics. And then I will link the JavaScript file. Let's load this in the browser. I'll try to make sure the JavaScript file is linked correctly by printing out something. Okay, there's the hello. And then I will give some styles to the canvas so I can see where it is. Give the body a gray background color. And then I'll give the canvas a white background color. Now let's give this body some padding so it looks less cramped. And then I'll give the canvas, I'll give the canvas the width and height of 500. Okay. And I'll make these variables so that I can use them later on. Grab the canvas. Okay. All right, so we have the canvas. We're ready to draw into it. Now we're gonna try to figure out how to plot points on here. We can have a function that plots a point somewhere on the canvas. And we can also do like when you click on any part of the canvas, it plots a point there. In order to draw anything onto a canvas, you first have to get a drawing context.
Okay.
Have you ever done any canvas programming before?
Yes, I made a snake.
Oh yeah, I remember that. So I'm gonna call it CTX for short. Don't have to spell out context all the way. And then the way you plot a point in Canvas is you actually have to use the arc function. So let me spell it out. I'm gonna do a dot right in the middle of the canvas. So 250 and 250. And then you specify the radius, right? Let's say 5. And then you have to say the starting angle and the ending angle. And the idea of the arc is you're drawing an arc like this.
Oh, okay.
And then this is your starting angle and this is your ending angle from the center, right? So
why are we drawing an arc?
Because I'm trying to draw a circle.
Oh.
They don't have a circle method in the canvas context for some reason. So I have to use an arc to draw a circle. So with a circle, what I'm going to do is I'm going to have the starting angle at 0. And then I'm going to say, hey, arc all the way around. So this should be the starting angle, comma, and then this should be the ending angle. So I'm going to have starting angle at 0 and the ending angle should be 360 degrees. But except we don't do it in degrees, we do it in radians. So what's the equivalent to 360 degrees in radians? It's 2 pi.
Okay, so do you put 2 pi there?
Yeah.
Oh, you do. Okay.
Luckily, you don't have to type pi. But this just draws the arc. It doesn't fill it in. Once you draw this arc, in order to fill it in, you actually have to say, start a path before you draw the arc, and then draw the arc, and then you say fill. And then it'll look at the path you've drawn, and then fill in the inside. You'll do that.
What if you don't close the arc?
If you don't close the arc, I think it'll automatically close it. It draws an extra line between your start point and end point. So I'm going to say begin path. And then after drawing the arc, I'm going to say fill. And let's see if that works. There's my dot here. There's my little dot. So that's how I'm going to plot points. I'm going to extract this guy into, I'm going to call this X and Y. I'll call this the radius. and then I'll put this inside a function. I'll call it plot point. Takes X and Y and a radius, and I'll default the radius at 5 pixels wide. And that's my plot point, and now I can call plot point. I'll go 200, 210.
All right.
And now I can plot points anywhere. Cool. Now let's do a mouse handler so that anywhere I click on the canvas, it'll plot a point there. Actually, I'm gonna do one dead in the center first, using the default radius.
Okay.
And then I'm gonna do canvas at event listener. Click. And the event object has a offset X, which we'll use as our X coordinate. The reason we want to use offset X is because it's offset from the top left corner of our canvas. If it were just the mouse X, it probably would be starting from the top left corner of the whole window, but we want it to be relative to the corner of our canvas. So we use offset X. Okay, now we have the XY. Let's just print that out just to know what it is. And we'll also just call plot point. That works. Cool. Now what we want to do is convert the coordinate system. I happen to know from experience that the top level of the Mandelbrot set image, the sort of global view, as I described, that lies within these bounds, -2, 2 in the X direction, and -2 and 2 in the Y direction. And this is 0, 0 coordinate. So we're looking at like a Cartesian coordinate system.
Oh, I see.
And I happen to know the Mandelbrot set is like somewhere here. Okay, so if we want to get that view, then what we want to do is sort of scale our canvas's coordinate system to these bounds. Now our canvas's coordinate system is actually 0, 0 on the top left-hand corner. And then because I made the canvas 500 by 500, it's going to be 500 at the end here, going across, and then it's going to be 500 over here, right? We'll call this coordinate system the screen coordinates. And then once we convert it into that -2 to 2 region, we call it the world coordinate. And also one more thing. Like usually we call this the X direction, and then this is the Y direction.
Mm-hmm.
Instead of calling it X and Y, however, I'm gonna call it R, standing for real, and then I, standing for imaginary.
Okay. Why?
Because it turns out that what we're plotting are actually complex numbers. When we're dealing with the Mandelbrot set, what we're visualizing is actually the space of all complex numbers.
What is complex numbers?
What is complex numbers? Complex numbers are numbers that have a real part and an imaginary part. A is the real part,
Mm-hmm.
and B is the imaginary part.
Right.
And the imaginary part is the part that is multiplied to I. And what is I? Well, I is the square root of -1. Square root of -1 is impossible because if you square any real number, it will not be a negative number. So there couldn't possibly be a thing which, when multiplied by itself, it gives you a -1, a negative number of any sort, right? Unless it's imaginary. So that's what I is. Some of you might have been taught imaginary numbers. I don't want to dig all the way into imaginary numbers. Maybe this is enough. There are interesting properties, though, about imaginary numbers. One of them is if you square I, or you square anything that's multiplied to I, you actually end up with a real number because if you square the square root of -1, you end up with -1, and then so that there's a way for imaginary number to go back into the real number realm by squaring it, and that is actually going to come into play later. So that's what I wanted to say about this number axis. We're actually plotting real on the horizontal direction and then imaginary on the vertical direction. If I want to convert the screen X to the coordinate in the world in the real direction, I'll call this R. I want to center this point at the middle of the canvas, right? Which would be width divided by 2. So what I want to do is X minus width divided by 2. And that's going to have the effect of centering it.
Right.
And then I want to multiply it by a scale factor. Whereas previously, this horizontal line spanned 500 pixels. Now I want it to span from -2 to 2, which is just 4 ticks.
Yeah.
So each tick is 125 pixels.
Yep.
So that's what I'm going to use.
Okay.
So I'm going to say after this adjustment, this subtraction, I'm going to multiply it by the scale factor. And the scale factor is going to be 1 over 125.
Okay.
And that gets us the R. And then the imaginary part is similar. I just do it in the other direction. Okay. And then now I'm going to see whether we get the right answer. I'll just print them out. Okay. This should be 0, 0. Close enough. And then this should be close to 2. Oh, except the I direction is negative. I want it to be positive in this quadrant and negative. So I'll just flip the sign on the I. So now both R and I are positive in this quadrant. This one, the I is negative. That's what I want. And then this one, both of them are negative. And then this one, the R horizontal direction is negative, but the I vertical direction is positive. So this is what I want. So now I have a way to convert from the screen coordinate to the world coordinate. I'm going to make a function that does that for me. I return both of the numbers in an array like that. I also want to convert the other way as well. So I want to convert from the world to screen. And to do that, the calculation is going to be exactly inverse. So I'm going to do, starting from R, we want to divide by the scale factor, looks like. And then I want to add the width divided by 2. Okay, I hope this works. I'm going to do
36. Should that be like minus? Not this.
This one?
Plus. It shouldn't be the same because you revert it. So it's minus.
Oh, yeah. Good point. Yes, thank you. So I should do that first. Yeah. I want to just verify that I got these correct. Well, I already tested this one. So I'm going to assume the screen to world is correct. But I want to make sure the other direction is correct. So I do it. I have it come back and print them out and see if we get the correct answer. Has already been declared. Oh. Okay. Yeah, the original XY is same as the new XY. That's the original XY. That's the after being converted there and back. Okay, so I'm happy with these functions. So we're able to convert coordinates now. Oh, one more thing. I want to have a function that plots a line as well. It'll come in handy a little bit later on. And the way you plot a line is you begin a path. And then you say move to one location. And then you say line to the second location.
Okay.
And then you say stroke. And that's how you plot a line. Maybe now I make it when you click, it's going to plot a line from 0, 0 to your point. See if that works. Yeah.
Well.
Oh yeah, that actually makes sense. I was thinking 0, 0 is in the center, but it's
okay.
but it's not in screen coordinates. 0, 0 is the top left corner.
Yeah.
So this is correct. I guess I could do 250. And that would come out from the center.
Whoa.
Okay, so pretty cool. Now we're gonna start doing the iteration. The formula that makes this thing work, the Mandelbrot set work, is this. I think they write it like this. This sign that says going back and forth, it means you take the output of the function and then you feed it back into the input. This is actually a numeric sequence. Z of 0 is always 0.
Okay.
And C is a constant. It's some number. It's a complex number. Both Z and C are complex numbers. They could potentially have an imaginary part. But C is the point on the canvas that is being plotted. So like if we pick that point, that is the C. And for each point on the canvas, we're going to get a C constant to be used in this formula. And FC means we're applying this function specifically for that constant C.
If you have a point on the screen, but you will have 2 coordinates, how does this count work?
Oh, okay. If I do that, then my C is basically that.
Oh, you add them together?
It has a real part and an imaginary part. That is C equals 0.856 plus 1.12 times I.
Oh, there's still the I. Okay, gotcha.
And normally when we think of a Cartesian coordinate system, we think of X and that's Y, but here it's still 2 numbers. It's just one is the real part, one is the imaginary part.
Gotcha.
So that's how C is arrived at. First, we pick the C. And just to have a simple example, we're going to use a simple number. Say C is 1. And it has no imaginary part because we're just keeping it simple for now. This is Z, not to be confused with 2. Z0 is always 0. Okay. So we start calculating this formula with Z equal to 0. So 0 squared is 0. Plus C, which is 1, is going to be 1. F of 1, because C is 1, F of 1 of 0 is 1. Okay. Because of this this two-way thing, which means we take the output of the function, we feed it back into the input in order to get the next number in the sequence. And then we do the equation again. So 1 squared is 1 plus C, which is 1, we get 2.
The F2, why?
Sorry, that was a mistake. This is still F1 because C1 is the constant. Good catch. And then still F1, but with Z equal to 2 now because we feed the output back into the input. And now we're going to get 4 plus 1, which is 5. And we do it again. 25 plus 1, 26. You can see very quickly this is gonna get really big. As this z increases, this number is going to infinity. The limit of the sequence is going to infinity. And it turns out that the Mandelbrot set, its definition has to do with whether this number will grow to infinity or not. So to give you an idea, it's like a number for c that will not go to infinity would be c equals 0. If c was 0,
if c is less than 1, then it's not gonna go to infinity. Is that true?
That's not exactly true, because let's just do it in code. and we will see. So let's do this. So we convert the screen coordinate to the world coordinate here whenever we click. And then what we're going to do is do the iteration. Let's iterate a number of times. I'll call this k. Let's do it 7 times for now. We're going to initialize z. There's a z real part. I'll call it zr.
Okay.
Actually, I'm going to call this CR for the real part of C and the imaginary part of C. So there's a CR and a CI. The real part of Z starts at 0, and the imaginary part, because Z of 0 is always 0. But for now, don't worry about the imaginary part. I'm going to comment that out for now. And then we're going to say, hey, the next version of ZR is ZR times itself squared. And then we're going to add CR to the equation. And again, I'm ignoring the imaginary part just for now.
Okay.
And then we're going to do that 7 times. But each time I'm actually going to plot the point. I'm going to convert it to the screen coordinates.
Okay.
World to screen. For the imaginary part, because I want to ignore the y coordinate, I'm just going to say height divided by 2, which is the center of the screen vertically.
Oh, okay.
The y, and then when we get to here, I'll just use the c's coordinate, which will be the center of the screen always.
Okay.
And then I'll plot, see what that looks like. Okay. Maybe
out the coordinate, the coordinate.
So if I click on 0, it stays at 0. 0 squared is 0. 0 plus 0 is 0. So if you click 0, it basically stays there. So that's an example of a number that will not go to infinity. There's a rainbow color scheme that I prepared. And what I'm going to do is get a color. K-mod colors length.
Okay.
To tell the canvas that I want to use this color, I'm going to say fill style equal this color.
Oh, whoa.
Okay, so this is the colors of the rainbow. I'll put it on the side here. Where's the red color? Did I do it wrong? I don't see the red.
Yeah.
That's red though. Oh, did I plot the point at the beginning? Oh, maybe the first point I'm gonna plot it black.
Okay.
Oh, I see red now. Okay. Okay, so each time I iterate, I plot that point with a different color, basically. So and based on the order of the colors of the rainbow, we can kind of see which one happened first and then second, etc. So if we go here, no, maybe here. Because, oh wait, why are we going from, oh, I don't want to do this one. I don't want to plot that line. Wait, why is it always plotting the point at the center? I didn't mean, oh, because of that. Forgot. Okay, so what I'm going to do is clear the canvas at the beginning.
Okay.
so that each time I click, it'll erase the previous one. And now you can actually see. And actually, I'll change this to the mouse move even.
Whoa.
Let's start with the 0. So if you're near 0, then it just converges to 0 very quickly. That's obvious. If you get a little bit more past a certain point, you can see it's going to infinity. Like, and then, yeah, that's definitely going to infinity. Even here, it's probably already going to infinity if I just increase the number of times you iterate.
Mm-hmm.
Yeah, it's like, bam. And this is R equal to 0.216. This is an interesting point of, this is -1. F of -1 with 0. So this is the formula. Well, -1. -1 squared is 1, and then -1 is 0. And then you plug 0. Oh, sorry. Yeah, you plug 0 back in, and then 0 squared is 0. -1, you get -1.
It's going to be back to 0.
Yeah, so it's going to oscillate between 0 and -1. And you can see that here. You put -1 here, you see 2 points, one at -1, one to 0. But in between, you can see these, it's still jumping back and forth, but then sometimes they're closer, sometimes they're farther apart.
That's interesting.
Yeah. And then here, it splits into 4. And then actually at some points it probably splits into 8 and 16 and so forth. It's really mesmerizing. It's kind of crazy how it works.
You go to the negative direction, it's going to split into more parts. But if you go into the positive, it's only going one direction.
Well, in negative direction, only some, because if you go greater than 2, it's blowing up for sure. Although that's not in our view.
I think the dot itself is cool, even just from like one direction.
Yeah, even one direction is already fascinating. Feigenbaum constant. Bifurcation. What we're seeing here is this bifurcation. And this happens in the population of animal in the wild. They use rabbits as an example, usually. As the rabbits population grow more, eventually they exceed the capacity of the resources that can support the rabbits. So then the next year, the population will decline because of that. So there's these two forces that's driving the population. But there can be scenarios where the population number oscillates from year to year. Like 1 year is one number, then the next year is lower, and then the next year is higher again, back to the original number. And then the next year is back to the lower number again. That's called bifurcation, and that's what's happening here. The number is oscillating, just jumping back and forth between 2 spots, but you can get into a condition where it bifurcates again into 4 spots, and that's what's going on. But you can bifurcate even more. I probably have to put my mouse at a very specific location to get the 8 spots. The same thing that's happening with the rabbit population is happening here. This bifurcation is jumping back and forth between 2 spots or 4 spots or 8 spots or even 16 spots and even more. And then when they graphed it, it looks like this thing.
Whoa.
And like this is where it bifurcates between 2 things, and then here the 2 split again into 4, and then later on they split again, and then again, and then again. That's like extremely fascinating, and this phenomenon exists in the Mandelbrot set as well.
I think it's interesting how they like compare the shape of whatever the formula is to like a real life data. I think that's very fascinating because it seems to be so random. Like why this rabbit data can be exactly the same shape as this mass format shape. I show you the wave, like the Japanese wave, and it just similar to the Mandelbrot set.
Yeah.
But it's completely like, I shouldn't say it's random, but it's just fascinating why it's like how the nature can work out this.
Yes, phenomenon that happens in very different scenarios, very, very different settings that seems to be completely unrelated.
Yeah, exactly.
But you see the same pattern.
Yeah.
Mm-hmm. It's extremely fascinating. And that's one of the reasons I'm enjoying this. I'm really into this.